Okay, in this lecture we're going to begin our section 6.2 material on solution of initial value problems using a Laplace transform. So in this section we're going to show how we could use the Laplace transform to solve initial value problems for linear differential equations. So let's start with the following result. This is theorem 6.2.1 from your textbook. Which is sometimes referred to as the lifting property of the Laplace transform. And it gives us a way to define the Laplace transform of the derivative of a function in terms of the original function. So here, since we're working with differential equations, which involve the derivative or derivatives of functions, when we take a Laplace transform of a differential equation, we need to know how to find the transform of a derivative. And here's what this theorem says. Suppose that we have a function f, which is continuous and of exponential order. So let's say the magnitude of our function is bounded above by k e to the at for t sufficiently large. And let us also suppose that the derivative f prime is piecewise continuous on any interval from 0 to a. So essentially piecewise continuous from 0 to infinity, since a could be any number. Then the Laplace transform of the derivative f prime exists for certain values of s, and the Laplace transform of the derivative f prime is given by s times the Laplace transform of the original function f minus the value of that function f at time 0. So this result is an important result which we will use throughout chapter 6. So let's prove this. We are looking here for the Laplace transform of the derivative of some function, f prime. So by definition, that is the integral from 0 to infinity of e to the negative st times the function I'm taking the transform of, which was f prime dt. Now here I'm trying to integrate a product, and our usual technique for integrating products would be the method of integration by parts. So to use that method, we need to define part of our integrand as u, and the rest of it as dv. So here, if I choose u as e to the negative st, then dv would be f prime of t dt, and du would then be negative s e to the negative st dt, and v would be my antiderivative of f prime. So the antiderivative of the derivative of f gives me back f. And so we then have the Laplace transform of f prime, which was this integral, using integration by parts is given by u times v. So I would have e to the negative st f of t. We're evaluating from 0 to infinity, minus the integral from 0 to infinity of v du. So for v times du, I have a negative s, which I can bring out in front, giving me positive s times the integral of e to the negative st f of t dt. And so let's see what we have. Evaluating this first expression from 0 to infinity, well, as t becomes infinitely large, the exponential e to the negative st will decay to 0, at least for some values of s. And then we subtract what we get by substituting in t equals 0, which would be e to the 0, or 1, times f of 0. And then we are adding s times this integral from 0 to infinity of e to the negative st f of t dt, which is the exact definition of the Laplace transform of f of t. So simplifying and rearranging these terms a little bit, I have s times the Laplace transform of f of t minus f of 0. And this is what we wanted to prove. So we see here that the Laplace transform of the derivative of a function can be rewritten in terms of the Laplace transform of the original function f and the value of f at time 0. Now, of course, when we talk about differential equations, we could have equations involving, say, the second or third derivative or higher order derivatives. So let's see if we can extend this result to the Laplace transform of higher derivatives. So next up, let's look at the second derivative. Suppose that f and f double prime satisfy the same hypotheses imposed on f and f prime from theorem 621. Then the Laplace transform Laplace of f double prime exists for some values of s, and the Laplace transform of f double prime is given by s squared times the Laplace transform of f minus s times f of 0 minus f prime of 0. So to prove this, let's take a look. We have, for the Laplace transform of the second derivative, well, the second derivative is just the derivative of f prime, my first derivative. So by using the lifting property, the Laplace transform of my second derivative would be s times the Laplace transform of the function I was taking the derivative of. So to get f double prime, I was taking the derivative of f prime minus the value of that function at t equals 0. So minus f prime of 0. And so using the lifting property a second time, I have s times the Laplace transform of f prime is s times the Laplace transform of f minus f of 0. And then I still have my minus f prime of 0 on the end. So distributing the s, I have s squared times the Laplace transform of f minus s times f of 0 minus f prime of 0, which is what we wanted to prove. So I could continue this process to find the Laplace transform of the third derivative of a function, or the fourth derivative of a function, and so on. And we arrive at the following corollary. Corollary 622, which follows by repeated application of the lifting property. And it says if we suppose that the functions f prime up through the n minus first derivative are all continuous and of exponential order, And if we suppose that the nth derivative is piecewise continuous on any interval from 0 to a, then the Laplace transform of the nth derivative of our function exists for some values of s, and the Laplace transform of the nth derivative of a function is given by s to the n times the Laplace transform of f minus s to the n minus 1, f of 0, and so on, up through minus s times the n minus second derivative at 0, minus the n minus first derivative at 0. So by repeated application of this lifting property, we see that we can rewrite the Laplace transform of the derivative of a function, or higher derivatives of a function, in terms of the Laplace transform of the original function and the value of this function and its derivatives at time 0. Now, the next thing that we're going to discuss in this section, before we can start seeing how the Laplace transform is used to solve initial value problems, is the concept of an inverse Laplace transform. So let's look at a definition here. Suppose that we have a function f of t, which has a Laplace transform given by capital F of s. Then we would say that the function little f of t is called the inverse Laplace transform of capital F of s, and we denote this as script L inverse of capital F of s is equal to little f of t. So for an inverse transform, we're given a function capital F of s, and I'm asking, well, what function has that as its Laplace transform? Or to illustrate a bit better here, we have some function little f of t, and we could define its Laplace transform as some function capital F of s, and an inverse Laplace transform acts in the opposite direction. If we are given capital F of s, we would take the inverse transform to see what we have for little f of t. So the idea of finding a transform or inverse transform is similar to, in calculus, finding a derivative versus an antiderivative. And one important property of the inverse Laplace transform is that it is linear. So as a note here, since we have seen that the Laplace transform is a linear operator, we saw that at the end of section 6.1, it follows that the inverse Laplace transform is also a linear operator. So that is, to find the inverse transform of a linear combination of two functions, say c1 f1 plus c2 f2, we could take a linear combination of the inverse transforms of f1 and f2. So in other words, to find an inverse transform of some linear combination of functions, I can take the inverse transform term by term. So before we look at some examples of finding inverse Laplace transforms for some different functions, I'll mention in your textbook, as well as on the course website, we have a table of some elementary Laplace transforms, which will be extremely useful throughout Chapter 6, and in particular for finding inverse transforms. So let's take a quick look at it here. The following table that I'm showing here is the table that's given in section 6.2 of the Boyce and DePrima textbook. It's also found on the course website. And the way that this table is organized, it's divided into two columns. Our left-hand column gives us a function little f of t, and the right-hand column gives us the Laplace transform of that function, which we call capital F of s. So some of these properties we've already established in section 6.1. In the examples we looked at, we saw that the Laplace transform of 1 is 1 over s for s greater than 0. We saw the Laplace transform of e to the at was 1 over s minus a for s greater than a. And we saw that the Laplace transform of the sine function, sine of at, is a over s squared plus a squared for s greater than 0. And we have also established in the first part of this section, 6.2, the last property in this table, the Laplace transform of the nth derivative of a function is given by s to the n times the Laplace transform of the original function, minus s to the n minus 1 f of 0, and so on. And then through some of your homework problems, you are going to derive some of these other properties in the table, and we will see some of these other properties as we continue to work through chapter 6. But this table will be extremely useful throughout chapter 6 when we are working with Laplace transforms. Now, we can also think about using this table to find an inverse transform, because if we look at a function in the right-hand column, that is a function f of s, by determining its form, we could see which function little f of t in the left-hand column has that function f of s as its Laplace transform. So let's look at some examples of this now. In section 6.2, this first example asks us to find the inverse Laplace transform of each function. And in part A, I have the function capital F of s is 4 over s minus 1 cubed. And I want to know what function has that as its Laplace transform. So I'm going to try to make use of one of the properties in that Laplace table to get my inverse transform. And I'll mention that when we're doing this, it is often useful when we're trying to determine which property from the table we're going to use to look at the form of the denominator of this f of s function. Here our denominator is s minus 1 cubed. So looking at our Laplace table, in that right-hand column, I want to try to find a function that has a denominator that looks like s minus some quantity all raised to a power. And looking through these properties, I can see that number 11 has a denominator that involves s minus a all being raised to some power, n plus 1, where my numerator is n factorial. And this is the Laplace transform of t to the n, e to the at, where n is a positive integer. So in order to make my function look more like what's given in this Laplace table, let's rewrite it in that exact form. So my denominator, s minus 1 cubed, well, I can think of that as s minus 1 raised to the 2 plus 1 power. so that n is 2. And to use that property in my Laplace table, well, I need the numerator of this fraction to be n factorial, or 2 factorial in this case. So in order to get 2 factorial as my numerator, well, I could think about taking the numerator that I had, which was 4, and then multiplying by 2 factorial and dividing by 2 factorial. So this gives me f of s is 4 divided by 2 factorial, which leaves me 2, times 2 factorial over s minus 1 to the 2 plus 1 power. And so for my function little f of t, which would be the inverse transform of capital F of s, well, using the linearity of the inverse transform, I can think about this as 2 times the inverse transform of 2 factorial over s minus 1 to the 2 plus 1 power. And so I have 2 times the inverse transform of this expression, which would be t to the n, where n was equal to 2, times e to the at, where a is 1. So I have the following expression for my inverse transform, and here we were using property number 11 in our Laplace table. So as a reference for your notes, you might write down which property we made use of there. So looking at another one, in part B, we have capital F of s is 2s minus 3 over s squared minus 4. And again, I'm going to look at the form of the denominator when I'm trying to decide which property from my table I'm going to use. So I see here that my denominator, s squared minus 4, is a difference of squares. It's s squared minus 2 squared. So when I look at my Laplace table, and I'm looking at which properties have a denominator that involves a difference of squares, I see that properties number 7 and 8 have a denominator of s squared minus a squared, where the numerator is either the constant a or s. And these are the Laplace transforms of the hyperbolic sine of at or hyperbolic cosine of at. So looking back at our function, let's try to rewrite it so that it looks like the properties that we have in our table. So here my numerator involves both s, 2s, and a constant 3. So let me maybe start by splitting up this fraction as 2s over s squared minus 4 minus 3 over s squared minus 4. Or for this first term, well, I could think about factoring out a 2, leaving me with s over s squared minus 4, which looks just like property number 8 for the hyperbolic cosine function. And then minus for this next term, well, my denominator is s squared minus 2 squared. And so I want the numerator to be the same number a that's being squared in my denominator. In this case, I want my numerator to be 2, since we had s squared minus 2 squared. And so to get a numerator of 2, I could take the numerator that I had, 3, and then multiply by a factor of 2 and divide by a factor of 2. And now each of these terms looks exactly like properties number 7 and 8 from our Laplace table. So I'm ready to find my inverse transform, f of t, which would be 2 times the inverse transform of s over s squared minus 4 minus 3 halves of the inverse transform of 2 over s squared minus 4. So this gives me 2 times the hyperbolic cosine of 2t minus 3 halves times the hyperbolic sine of 2t. And again, for the purposes of your notes, we are using properties number 7 and 8 in the Laplace table. So again, I mentioned at the end of this page that this table of elementary transforms can be found in your text or the course website. And using this table makes it much easier to find inverse Laplace transforms. Now let's look at some other examples here. One thing that we will often have to do when finding inverse transforms is rewrite a product of functions in terms of a linear combination to find my inverse transform term by term. So what we will see is that it is often useful or necessary to find a partial fraction decomposition in finding the inverse Laplace transform of a rational function, that is a quotient of 2 polynomials. So let's look at an example of this. Here we're asked to find the inverse Laplace transform of this function. And the first thing I do is to look at the form of my denominator. Here I have a denominator which is a quadratic, but it's not a sum or difference of squares. But it could be factored down to linear terms. So by factoring this denominator, I could rewrite it as s plus 2 times s minus 3. And so I could think of this function f of s as kind of a product of 2 terms. I have something like 3s over s plus 2 times 1 over s minus 3. And so I might be tempted to take the inverse transform of each piece and then multiply those inverse transforms. However, that is not valid. The Laplace transform and inverse transforms are linear. So a transform or inverse transform of a sum or difference of terms is just the sum or difference of the transform or inverse transform. However, something important to note here, let me stress this in our notes, the inverse transform of a product of 2 functions, let's say f of s and g of s, is not simply the product of the inverse transforms. So when I see that my denominator is a product of terms, s plus 2 and s minus 3, I cannot simply take the inverse transform of each factor. I need to do something to rewrite this as a linear combination of terms. So here I could make use of a partial fraction decomposition. Where I would take this single rational function that I have, whose denominator is a product of two linear factors, and decompose it as a over s plus 2 plus b over s minus 3. And so to solve for a and b, I could multiply through by my common denominator, giving me 3s is equal to a times s minus 3 plus b times s plus 2. So if I expand on the right-hand side and collect like terms, I would have a plus b times s plus negative 3a plus 2b. And equating the coefficients, I find that a plus b, the coefficient of s, must be 3, and negative 3a plus 2b, the constant coefficient, must be 0. So from my first equation, it follows that b is 3 minus a. And if I substitute into the second equation, I have negative 3a plus 2 times b, which would give me 6 minus 2a is 0. So this gives me 5a is equal to 6. And so a is 6/5. And then substituting back into my b equation, I have 3 minus 6/5. Now 3 would be 15/5 minus 6/5 leaves me with 9/5. And so we find that our capital F of s function we were given has a partial fraction decomposition given by a, which is 6/5 over s plus 2, plus b, which is 9/5 over s minus 3. Or if I think about bringing these constants out in front of each factor, I have the following. So now, looking at my denominator of these respective terms, I see that I have a linear term, something like s plus 2 or s minus 3. And comparing with the properties in my Laplace table, I see property 2 has a function whose denominator is a linear term, s minus some constant, s minus a. So using that property to find the inverse transform of each term, I have a 6/5 times the inverse transform of 1 over s plus 2. Now that denominator s plus 2 I can think of as s minus negative 2. So it would have an inverse transform of e to the negative 2t plus 9/5 times e to the 3t. And again, here we are using property number 2 in the Laplace table. So we see here that when that denominator involves a product of terms, we might have to use partial fractions to rewrite that product as a sum or difference of smaller, simpler terms, and then take the inverse transform term by term. So let's look at another example of this. Here we are asked to find the inverse Laplace transform of the following function. And when I look at my denominator, I see that it involves some cubic, which could be factored by pulling out an s from each term, leaving me with s squared plus 4. And that s squared plus 4 can't be factored down to linear terms. So I see that my denominator involves a product of two terms, a linear and a quadratic factor. But since the inverse transform of a product is not just the product of the inverse transforms, I need to use partial fractions to rewrite this as a linear combination of terms. So let's look at it. Here we have 8s squared minus 4s plus 12 over s times s squared plus 4. And this would have a decomposition of the form a over the linear factor s plus a linear function bs plus c over the irreducible quadratic factor. So multiplying both sides by my common denominator, s times s squared plus 4, I have 8s squared minus 4s plus 12 is equal to a times s squared plus 4 plus bs plus c times s. Or expanding on the right-hand side and collecting like terms, I have a plus b s squared plus cs plus 4a. And so equating the coefficients, I find that a plus b, the coefficient of s squared, has to be 8. C, the coefficient of s, is negative 4. And my constant coefficient, 4a, has to be 12. So it follows from the last equation that a is 3, and then substituting into my equation for b, b is 8 minus a, which would leave me with 5. So we find that capital F of s, our given function, has a decomposition of the form a, which was 3 over s, plus b, which is 5 times s, plus c, which was negative 4, all over s squared plus 4. And for each of these terms, when I look at the denominator, I have a denominator that is either s or a sum of squares, s squared plus 2 squared. So looking at my Laplace table, I'm going to be making use of property 1, where I have a denominator that is simply s, or properties number 5 and 6, where my denominator is a sum of squares, s squared plus a squared. So rewriting these terms of f of s to look exactly like what I have in my Laplace table, f of s can be rewritten as 3 times 1 over s plus 5s over s squared plus 4 minus 4 over s squared plus 4. Or for these last two terms, well, I could think about factoring out a 5 from the second term, leaving me with s over s squared plus 4. And then minus for the last term, well, my denominator is s squared plus 2 squared. So I want my numerator to be a, the value that was being squared, in this case 2. So to make that numerator 2, I can take the numerator that I had, 4, and then multiply and divide through by 2. So I have 3 times 1 over s plus 5 times s over s squared plus 4 minus 2 times 2 over s squared plus 4. And so taking my inverse transform, term by term, I have 3 times 1 plus 5 times cosine of 2t minus 2 times sine of 2t. And here we are using properties number 1, 5, and 6 from the Laplace table. Let's look at a couple of other examples to illustrate some other techniques for finding inverse transforms. I'll mention here that it is sometimes necessary to complete the square when finding an inverse Laplace transform of a rational function. So let's look at some examples of this. Here we are asked to find the inverse Laplace transform of each function. And in part A, we have f of s is 7 over this quadratic. And so when I look at my denominator, I see that I have a quadratic which is not, it can't be factored down to linear terms. And it's also not a sum or difference of squares. It doesn't have the form s squared plus a squared or s squared minus a squared. But all of the properties in our Laplace table where we have a quadratic denominator involve either a sum or difference of squares. So here we can't use partial fractions to simplify this any further since it's not factorable. And it also does not have a denominator that is a sum or difference of squares. But if I complete the square, for this quadratic denominator, I can rewrite it as the sum of squares. So let's look at it here. We have f of s is 7 over, completing the square, I have my s squared plus 2s terms, and then my plus 10 I can think of as being on the end. And so by completing the square, to my s squared plus 2s terms, I ask myself, what could I add so that this would then be factored as a perfect square? And so I would take half of my s coefficient, so half of 2 squared gives me 1, and add that to the end. And then to get a constant of 10 in the denominator in total, well, since I've already added plus 1, I need a plus 9, so that altogether I get that plus 10 value. And doing this allows me to factor the first part of my denominator as s plus 1 quantity squared plus a 9, which is 3 squared. So now looking at the form of my denominator, I have s plus 1 squared plus 3 squared. So let's take a look at our Laplace table. I see that properties number 9 and 10 involve some linear factor, s minus a squared plus b squared, where my numerator is either the number b or the factor s minus a. These are the Laplace transforms of e to the at times either sine or cosine of bt. So going back to our function and rewriting it in the exact form to use these properties, well, my denominator is s plus 1 squared plus 3 squared, and I want my numerator to be b, the number that was being squared, in this case 3. And so to get that number as my numerator, I would take the numerator that I had and multiply and divide by 3. So we arrive at the inverse Laplace transform. F of t is our constant 7/3 times the inverse transform of this expression, which would be e to the negative t times sine of 3t. And then similarly, looking at part B here, we have f of s is 3s minus 2 over s squared plus 6s plus 13. And so looking at that denominator, I see that I have a quadratic which cannot be factored down to linear terms, but is also not a sum or difference of squares. But if I complete the square, I can rewrite this as a sum of squares. So let's take a look at it. Here, f of s is 3s minus 2 over, well, if I think about my s squared plus 6s being together, I ask myself, what would I need to add to that quantity so that it could then be factored as a perfect square? So here, the value that I would add is half of my coefficient for s squared. So here, half of 6 would be 3 squared, gives me a 9. And then to get a total value of 13 as the constant in that denominator, I need to add another 4 onto that factor of 9 to keep it equal to 13. And so this now allows me to factor that first term in the denominator as s plus 3 quantity squared, with my plus 4 on the end. And my numerator, which is 3s minus 2, well, this first factor, instead of s, I need it to be the same factor that's being squared in the denominator, s plus 3, to use my property from the Laplace table. So for that leading term in the numerator, I'm going to replace s by s plus 3. And since I multiplied by a factor of 3 out in front, I have altogether 3s plus 9. So I've added 9 in the denominator, which means that I also need to subtract 9 in the numerator to keep this function the same. So I have my minus 2 and then an additional minus 9. So this gives me 3 times s plus 3 minus 11 over s plus 3 squared plus 4, or 2 squared. And so splitting this fraction to try to rewrite it in the exact form of the properties we're trying to use, I could take 3 times s plus 3 over s plus 3 squared plus 2 squared, and then minus, for this last term, I want my numerator to be the same number that was being squared in my denominator, that is 2. And so to get that constant, I would take my numerator of negative 11 and multiply and divide by 2. So this results in an inverse transform of 3 times e to the negative 3t times cosine of 2t minus 11 halves e to the negative 3t sine of 2t.